Imagine standing at the edge of existence itself, where space bends so violently that time itself comes to a halt, where the very fabric of reality tears apart, creating wounds in the universe so deep that nothing, absolutely nothing, can climb back out once it falls in. This is not science fiction. This is science fact. Black holes are regions of space where gravity overwhelms everything. They are the universe's ultimate prisons, cosmic monsters that devour light itself. Nothing, not light, not time, not information, escapes once past a certain point. They represent the most extreme conditions imaginable, places where the familiar rules of physics are pushed beyond their breaking point. But inside, it gets stranger. What happens in a black hole may hold the key to understanding space, time, and the nature of the universe itself. These mysterious objects challenge everything we think we know about reality. They force us to question the very foundations of physics, pushing us to explore ideas that seem impossible, yet may be profoundly true. Some scientists believe black holes are gateways to other dimensions. Others think they might be cosmic recycling centers, breaking down matter and energy into their most fundamental components. Still others propose they could be the birthplaces of new universes, cosmic wombs where entire realities are born from the death of stars. The journey into a black hole is a journey into the unknown, a voyage to the very limits of human understanding. It is a trip from which no information returns, no signals escape, no messages can be sent back to tell us what lies within. Yet through the power of mathematics, theoretical physics, and our deepest insights into the nature of reality, we can peer into these cosmic abyss and begin to understand what might await anything brave enough or unfortunate enough to fall inside. To find out what happens inside, we first need to understand what a black hole actually is. Picture the most massive star you can imagine, a giant so enormous that our sun would look like a grain of sand beside it. This stellar behemoth burns through its nuclear fuel for millions of years, creating a delicate balance between the outward pressure of fusion reactions and the inward pull of its own immense gravity. But all stars, no matter how massive, eventually run out of fuel. And when they do, gravity wins. In the final moments of a massive star's life, something extraordinary and terrifying happens. Without the outward pressure from nuclear fusion to hold it up, the star begins to collapse under its own weight. But this is not a gentle, gradual collapse. This is a catastrophic implosion that happens in less than a second. Imagine an object 30 times more massive than our sun, crushing itself down to a point smaller than a city. The density becomes so extreme that a teaspoon of this matter would weigh as much as Mount Everest. This is how most black holes are born. They emerge from the death throes of the universe's most massive stars, created in the most violent events imaginable. But the story does not end with the star's death. In fact, it is just the beginning of something far more mysterious and profound. A black hole forms when mass is compressed into an extremely small space. The gravitational field becomes so intense that it warps space-time itself, creating a region where the normal rules of physics begin to break down. Think of space-time as a stretched rubber sheet. Place a bowling ball on it, and it creates a depression. Roll a marble nearby, and it will curve around the bowling ball, following the bent contours of the sheet. Now imagine pressing that bowling ball down so hard that it creates not just a depression, but a hole that goes infinitely deep. That is what a black hole does to the fabric of space and time. The boundary around a black hole is called the event horizon. This is the point of no return, the cosmic equivalent of a one-way door. Cross this invisible barrier, and there is no going back, no escape, no second chances. The event horizon is not a physical surface you could touch or land on. It is simply a mathematical boundary in space, a line drawn by the laws of physics that separates the inside from the outside, the escapable from the inescapable. The size of the event horizon depends on the mass of the black hole. For a black hole with the mass of our Sun, the event horizon would have a radius of about 3 kilometers. But stellar mass black holes are just the beginning. There are black holes out there with masses millions or even billions of times greater than our Sun. These supermassive black holes lurk at the centers of galaxies, including our own Milky Way, where a black hole with a mass 4 million times that of the Sun sits like a sleeping giant. Then there are the intermediate mass black holes, mysterious objects that seem to exist in the gap between stellar mass and supermassive black holes. Scientists are still trying to understand how these form and why they seem to be relatively rare compared to their smaller and larger cousins. But perhaps the most intriguing are the primordial black holes, theoretical objects that may have formed in the very early universe, not from collapsing stars, but from extremely dense regions of matter that existed shortly after the Big Bang. These could range in size from microscopic to stellar mass, and if they exist, they could help explain some of the universe's greatest mysteries, including dark matter. Inside the event horizon lies the singularity, the heart of the black hole, where all the collapsed matter is thought to be concentrated. According to our current understanding of physics, the singularity is a point of infinite density and zero volume, where the curvature of space-time becomes infinite and the laws of physics as we know them simply cease to function. It is a place where mathematics breaks down, where equations produce infinities, and where our deepest theories about the nature of reality encounter their ultimate limit. But here is the truly mind-bending part. Time itself behaves differently near a black hole. As you approach the event horizon, time slows down relative to the outside universe. This is not just a theoretical curiosity. It is a measurable effect predicted by Einstein's theory of general relativity and confirmed by countless experiments and observations. The closer you get to the black hole, the more dramatically time dilates, until at the event horizon itself, time appears to stop completely from the perspective of a distant observer. This creates one of the most fascinating paradoxes in all of physics. If you were to watch someone fall into a black hole, you would see them slow down as they approach the event horizon, their image becoming redder and dimmer until they appeared to freeze at the boundary, never quite crossing over. From your perspective, they would remain frozen there forever, gradually fading from view as their light became too red, shifted to detect. But from the perspective of the person falling in, something completely different happens. They feel nothing unusual as they cross the event horizon. Time passes normally for them. They do not slow down or freeze. They simply continue falling, unaware that to the outside universe they appear to be stuck at the boundary for all eternity. This is the first hint that black holes are not just exotic objects in space, but laboratories for testing the very foundations of our understanding of time, space, and reality itself. They force us to confront the strange and counterintuitive nature of the universe we live in, where time is not absolute, where space can be curved and warped, and where the familiar concepts of cause and effect can be turned upside down. Black holes come in different varieties, each with their own unique characteristics and formation mechanisms. Stellar mass black holes, formed from collapsed stars, typically range from about 3 to 20 times the mass of our Sun. These are the most common type we observe in our galaxy, often found in binary systems where they strip material from a companion star, creating brilliant accretion disks that spiral into the black hole like cosmic whirlpools. Supermassive black holes are the giants of the black hole family, containing millions or billions of times the mass of our Sun. These colossal objects reside at the centers of most galaxies, including our own Milky Way. The supermassive black hole at the center of our galaxy, known as Sagittarius A star, has a mass equivalent to about 4 million suns and an event horizon that could fit inside the orbit of Mercury. Despite their enormous size, these black holes are actually less dense than water when you calculate their average density across their entire volume. The formation of supermassive black holes remains one of the great mysteries in astrophysics. How did objects so massive form so early in the universe's history? Some theories suggest they grew from smaller seed black holes that formed shortly after the Big Bang. Others propose they formed directly from the collapse of massive gas clouds in the early universe. Still others suggest they could have grown through the mergers of many smaller black holes over billions of years. Intermediate mass black holes occupy the mysterious middle ground between stellar mass and supermassive black holes. These objects, with masses ranging from hundreds to thousands of times that of our Sun, are much harder to detect and understand. They do not create the dramatic fireworks of stellar mass black holes feeding from companion stars, nor do they anchor the centers of galaxies like their supermassive cousins. Instead, they lurk in globular clusters and the outskirts of galaxies, revealing themselves only through subtle gravitational effects. Then, there are the theoretical primordial black holes, objects that may have formed in the first fraction of a second after the Big Bang. Unlike black holes formed from collapsed stars, primordial black holes could have any mass, from microscopic to stellar scale. If they exist, the smallest ones would have evaporated long ago through a process called Hawking radiation, while larger ones could still exist today, possibly making up some or all of the mysterious dark matter that comprises most of the mass in the universe. The concept of an event horizon is perhaps the most important feature that defines a black hole. This invisible boundary marks the point where the escape velocity equals the speed of light. Since nothing can travel faster than light, nothing can escape from within this boundary. The event horizon is not a physical surface, but rather a geometric property of space-time itself. It exists wherever the gravitational field becomes so strong that light rays aimed directly outward are bent back inward. The radius of the event horizon, called the Schwarzschild radius, is directly proportional to the mass of the black hole. Double the mass, and you double the radius. This means that more massive black holes actually have less extreme conditions at their event horizons, while a stellar mass black hole would stretch and compress an astronaut with devastating tidal forces. A supermassive black hole might allow someone to cross the event horizon relatively unharmed, at least initially. Beyond the event horizon lies the ergosphere, a region that exists only for rotating black holes. In this zone, space-time itself is dragged around by the rotation of the black hole, making it impossible for anything to remain stationary relative to distant observers. This frame-dragging effect, predicted by general relativity, has been confirmed in much weaker forms around rotating bodies like Earth and has profound implications for our understanding of space-time. The singularity at the center of a black hole represents the ultimate frontier of physics. Here, according to general relativity, all the matter that formed the black hole is compressed to infinite density in zero volume. The curvature of space-time becomes infinite, and the equations that describe gravity simply break down. This mathematical catastrophe signals that our current theories are incomplete and that new physics, likely involving quantum mechanics, is needed to understand what really happens at the center of a black hole. But the singularity may not be a single point at all. For rotating black holes, general relativity predicts a ring singularity, a circle of infinite density and curvature. Some theoretical physicists have speculated that this ring might be a gateway to other parts of the universe or even other universes entirely, though such ideas remain highly speculative and unproven. The study of black holes has revolutionized our understanding of gravity, space-time, and the fundamental nature of the universe. They serve as natural laboratories for testing the most extreme predictions of general relativity and have led to discoveries that have profound implications for physics, cosmology, and our understanding of information and entropy. So what happens when something falls in? The answer to this question will take us on a journey through some of the most profound and beautiful ideas in all of science. Ideas that challenge our most basic assumptions about the nature of existence itself. Imagine you are an astronaut on a mission gone terribly wrong. Your spacecraft has malfunctioned, and you find yourself falling helplessly toward a black hole. What would you experience? What would you see? And perhaps most importantly, what would happen to you as you approach that invisible boundary known as the event horizon? The journey begins long before you reach the black hole itself. From a distance, the black hole appears as a sphere of absolute darkness, outlined against the star field behind it. But as you fall closer, something strange begins to happen. The stars behind the black hole appear to shift and distort, their light bent around the massive object in a phenomenon called gravitational lensing. The black hole acts like a cosmic magnifying glass, warping space and time so severely that light itself follows curved paths around it. As you continue to fall, you notice that time itself begins to behave strangely. You carry with you a clock, perfectly synchronized with mission control back on Earth. At first, everything seems normal. Your clock ticks at its usual rate, and you feel no different than you would floating in empty space. But if you could somehow communicate with Earth, you would discover something remarkable and terrifying. Your radio signals, when they reach Earth, would appear to be arriving more and more slowly. Your voice would sound deeper and deeper, stretched out in time like a recording played at the wrong speed. This is gravitational time dilation, one of the most profound predictions of Einstein's theory of general relativity. The deeper you fall into the black hole's gravitational well, the more time slows down relative to the outside universe. From your perspective, everything feels completely normal. Your heart beats at its regular rhythm, your thoughts proceed at their usual pace, and your clock ticks steadily. But to observers far away from the black hole, you appear to be moving in slow motion, speaking in slow motion, even thinking in slow motion. Meanwhile, something else is happening to your body, something that depends critically on the size of the black hole you are approaching. If this is a stellar mass black hole, formed from a collapsed star just a few times more massive than our Sun, you begin to feel an uncomfortable stretching sensation. Your feet, being slightly closer to the black hole than your head, experience a stronger gravitational pull. This difference in gravitational force between your head and feet is called a tidal force, and it grows stronger as you approach the black hole. At first, this tidal stretching might feel like a gentle pull, similar to hanging from a pull-up bar. But as you get closer to the event horizon, the forces become more and more extreme. Your body begins to stretch lengthwise while being compressed from the sides. Scientists have given this gruesome process a darkly humorous name, spaghettification, because you would be stretched out like a piece of spaghetti. The exact point at which spaghettification becomes lethal depends on the mass of the black hole. For a stellar mass black hole with the mass of our Sun, you would be torn apart long before reaching the event horizon. The tidal forces would overcome the molecular bonds holding your body together, reducing you to a stream of atoms falling toward the black hole's center. But here is where black holes reveal one of their most counterintuitive properties. If you were falling toward a supermassive black hole, the kind found at the center of galaxies, your experience would be dramatically different. These giants are so massive that their event horizons are enormous, sometimes larger than the orbit of Pluto. At such scales, the tidal forces at the event horizon are actually quite gentle. You could cross the boundary between inside and outside without feeling anything unusual at all. This seems to violate our intuition about black holes. How can something more massive be less dangerous? The answer lies in the relationship between mass and the size of the event horizon. While supermassive black holes have much stronger gravity overall, that gravity is spread out over a much larger volume. At the event horizon of a supermassive black hole, you are much farther from the center than you would be at the event horizon of a stellar mass black hole, so the tidal forces are correspondingly weaker. As you approach the event horizon, regardless of the black hole's size, you would witness one of the most spectacular light shows in the universe. Any matter falling into the black hole ahead of you would be heated by friction and compression, glowing brilliantly as it spirals inward. This glowing disk of material, called an accretion disk, can shine brighter than entire galaxies, powered by the conversion of gravitational potential energy into heat and light. The light from this accretion disk would appear increasingly blue shifted as you fall deeper into the gravitational well. High energy radiation, normally invisible to human eyes, would shift into the visible spectrum, creating a brilliant display of colors that no human has ever seen. At the same time, light from behind you, from the universe you are leaving behind, would appear increasingly red-shifted, growing dimmer and redder until it fades beyond detection. From the perspective of someone watching you fall from a safe distance, your story takes on an entirely different character. As you approach the event horizon, they would see you slowing down, your movements becoming more and more sluggish. The light from your spacesuit would become increasingly red-shifted, making you appear redder and dimmer. Eventually, you would seem to freeze at the event horizon, your image gradually fading as the light becomes too red-shifted to detect. To the outside observer, you would appear to remain at the event horizon forever, never quite crossing over, gradually becoming invisible as your light is stretched to longer and longer wavelengths. This creates one of the most profound paradoxes in physics. From your perspective, you cross the event horizon in a finite amount of time and continue falling toward the center. From the outside perspective, you never cross at all, remaining frozen at the boundary for all eternity. Both perspectives are equally valid. Both are consistent with the laws of physics, yet they describe completely different realities. This paradox reveals something deep about the nature of space and time near black holes. Time is not absolute or universal. It depends on where you are and how fast you are moving. Near a black hole, these effects become so extreme that different observers can disagree not just about when events happen, but about whether they happen at all. The event horizon itself is invisible and intangible. There is no physical barrier, no wall or membrane that you crash into. It is simply a boundary in space-time, a line drawn by mathematics that separates the region where escape is possible from the region where it is not. Crossing it would feel no different from crossing any other invisible line in space. You would not know you had passed the point of no return until you tried to turn around and discovered that every direction you could travel leads deeper into the black hole. This is perhaps the most terrifying aspect of falling into a black hole. There is no moment of realization, no dramatic threshold crossing, no last chance to escape. One moment you could theoretically fire your rockets and escape back to safety, and the next moment, without any warning or sensation, escape becomes impossible. The boundary between freedom and imprisonment is crossed in silence, marked only by the inexorable mathematics of general relativity. The mathematics behind these extreme effects were first worked out by Karl Schwarzschild, a German physicist and astronomer who derived the exact solution to Einstein's field equations for a spherically symmetric, non-rotating black hole. Remarkably, Schwarzschild completed this work while serving as a soldier on the Russian front during World War I, just months after Einstein published his theory of general relativity. Tragically, Schwarzschild died of an autoimmune disease contracted during the war, just days after completing his groundbreaking calculations. He never lived to see how his mathematical insights would revolutionize our understanding of the universe. The Schwarzschild solution revealed something that even Einstein found difficult to accept. It showed that at a certain radius, now called the Schwarzschild radius, the mathematics predicted a boundary where time dilation becomes infinite and space curvature becomes extreme. Einstein himself initially believed that such conditions could never actually occur in nature, that some physical process would prevent the formation of such extreme objects. It took decades for physicists to accept that black holes were not just mathematical curiosities, but real objects that could and do exist in our universe. As you continue your fall toward the black hole, you begin to notice other strange effects. The Doppler shift, normally associated with sound waves, becomes extreme for light waves. The cosmic microwave background radiation, the afterglow of the Big Bang that fills all of space, becomes increasingly blue shifted in the direction you are falling and red shifted behind you. If you could see it, the entire universe would appear to compress into a bright ring of light in front of you, while behind you, everything fades to darkness. The phenomenon of gravitational lensing becomes more and more pronounced as you approach the event horizon. The black hole acts like a gravitational lens, bending light around it in ways that create multiple images of distant objects. You might see several copies of the same star or galaxy, each following a different light path around the black hole. Some light rays circle the black hole multiple times before reaching your eyes, creating a complex web of images that overlap and interfere with each other. For a rotating black hole, called a Kerr black hole after mathematician Roy Kerr, who found the solution in 1963, the situation becomes even more complex. The rotation of the black hole drags space-time around with it, creating a region called the ergosphere, where it becomes impossible to remain stationary relative to distant stars. In this region, space-time itself is flowing around the black hole like water circling a drain, and anything within it must rotate along with the flow. The ergosphere extends beyond the event horizon, creating a zone where extraordinary things become possible. In principle, it might be possible to extract energy from a rotating black hole by dropping objects into the ergosphere and having them emerge with more energy than they entered with. This process, known as the Penrose process after physicist Roger Penrose, could theoretically allow advanced civilizations to use rotating black holes as cosmic power sources. If you were falling toward a rotating black hole, you would notice that your trajectory becomes increasingly complicated as you approach the ergosphere. Instead of falling straight inward, you would begin to spiral around the black hole, following the twisted geometry of space-time. The faster the black hole rotates, the more dramatic this spiraling motion becomes. The interior structure of a rotating black hole is also fundamentally different from that of a non-rotating one. Instead of a point singularity at the center, rotation creates a ring singularity, a circle of infinite density and curvature. Theoretical physicists have speculated that this ring might be more than just a mathematical pathology, that it might represent a genuine portal to other regions of space-time or even other universes entirely. As you approach ever closer to the event horizon, quantum effects begin to play an increasingly important role. According to quantum field theory, empty space is not truly empty, but filled with virtual particle pairs that constantly pop into existence and annihilate each other. Near the event horizon, the extreme curvature of space-time can separate these virtual particles, causing one to fall into the black hole while the other escapes. This process, predicted by Stephen Hawking in 1974, causes black holes to emit radiation and slowly evaporate over time. From your perspective, as you fall toward the black hole, you would not notice this Hawking radiation. The individual particles are far too small and sparse to detect directly. But from the perspective of distant observers, your black hole is slowly shrinking, returning its mass energy to the universe one particle at a time. For stellar mass black holes, this process is incredibly slow, taking far longer than the current age of the universe to complete. But for smaller black holes, if they exist, the evaporation process would be much faster and more dramatic. The final moments before crossing the event horizon depend critically on what else is falling into the black hole along with you. If you are the only object in the vicinity, your crossing might be relatively peaceful, at least for a supermassive black hole. But if there is significant amounts of matter falling in, the situation becomes much more violent and chaotic. Material falling into a black hole does not simply disappear quietly. It forms an accretion disk, a swirling maelstrom of superheated plasma that can reach temperatures of millions of degrees. This disk shines brilliantly across the electromagnetic spectrum, from radio waves to gamma rays. The magnetic fields threading through this plasma can become twisted and compressed, occasionally launching powerful jets of material away from the black hole at nearly the speed of light. If you were unfortunate enough to encounter this material on your way in, you would be vaporized long before reaching the event horizon. The radiation from the accretion disk alone would be lethal at enormous distances. The jets, if they happened to be pointed in your direction, would deliver a concentrated beam of high-energy particles and radiation that could sterilize entire solar systems. But assuming you somehow avoid these hazards and approach a relatively quiet black hole, you reach the moment of truth. The event horizon looms before you, invisible and intangible, yet representing the most profound boundary in the universe. As you cross this threshold, you pass from the realm of the possible into the realm of the inevitable, from a universe where escape remains an option, into a region where all roads lead to the same destination. But once inside, where do you go? What happens in that realm beyond the event horizon, where the normal rules of space and time no longer apply? The answer to that question takes us even deeper into the mysteries of black holes, to a place where space and time themselves become strange and unfamiliar, where the very concepts of up and down, future and past lose their familiar meaning. You have crossed the point of no return. Behind you lies the universe you once knew. Ahead lies the unknown. But here is the most shocking thing about crossing the event horizon of a black hole, at least for a supermassive one. You feel nothing. No barrier, no wall, no sudden change in the forces acting on your body. From your perspective, you have simply passed through an invisible boundary in space, as unremarkable as crossing an imaginary line on a map. Yet everything has changed in the most fundamental way possible. You are now in a region of space-time where the very concepts of space and time have been turned upside down, where the familiar rules of geometry no longer apply, where cause and effect take on new and strange meanings. You have entered a realm that challenges the deepest assumptions of human intuition about the nature of reality itself. Inside the event horizon, something extraordinary happens to the structure of space-time. In the normal universe, space has 3 dimensions and time has 1, and you can move freely through space in any direction, while being carried inexorably forward through time. But inside a black hole, this relationship becomes twisted in the most profound way imaginable. The radial direction, the direction pointing toward the center of the black hole, becomes time-like rather than space-like. What does this mean? In the everyday world, you can choose to move left or right, forward or backward, up or down. These are spatial directions, and you have the freedom to travel in any of them. Time, on the other hand, carries you forward whether you like it or not. You cannot choose to move backward in time any more than you can choose to stop aging. Inside a black hole, the inward radial direction becomes like time. Just as you cannot stop moving forward through time in the normal universe, inside a black hole, you cannot stop moving inward toward the center. This is not simply a matter of being pulled by gravity, as you might be pulled toward any massive object. This is something far more fundamental. The geometry of space-time itself has been altered so dramatically that all possible futures, all possible paths through space-time lead inevitably toward the singularity at the center. No trajectory, not even light itself, can move outward. The very concept of escape has become as meaningless as the concept of traveling backward in time. Imagine trying to explain this to someone who has never heard of relativity or curved space-time. You might say that inside a black hole, the center is not just down, it is tomorrow. Moving toward the center is not just falling, it is aging. The singularity is not just a place, it is a moment in your future that you will inevitably reach, just as inevitably as you will reach next Tuesday in the normal universe. This inversion of space and time creates some of the most mind-bending consequences in all of physics. Light rays, which normally travel in straight lines through space, find themselves trapped on trajectories that spiral inexorably inward. Every photon that enters the black hole, regardless of its initial direction, ends up falling toward the center. Even a beam of light aimed directly outward, away from the singularity, curves back around and joins the inward spiral. From your perspective, as you fall deeper into the black hole, the geometry of space becomes increasingly alien. The familiar Euclidean geometry you learned in school, where parallel lines never meet, and the angles of a triangle add up to 180 degrees, no longer applies. Space has become curved in ways that defy human intuition, folded and twisted by the immense gravitational field into shapes that have no analog in everyday experience. If you could somehow map the interior of the black hole, you would discover that it has a finite volume but no center in the usual sense. The singularity, which classical physics tells us lies at the center, is not a place you can point to and say, there it is. Instead, it is more like a moment in time, an inevitable future that awaits all matter and energy that falls past the event horizon. The journey from the event horizon to the singularity takes a finite amount of proper time, the time measured by clocks falling along with you. For a stellar mass black hole, this journey might take only microseconds. For a supermassive black hole, it could take hours or even days. But regardless of the black hole's size, the outcome is the same. Every trajectory leads to the same destination. Every possible future converges on the same point. As you fall deeper, the tidal forces that may have been gentle at the event horizon begin to grow stronger. Even in a supermassive black hole, the closer you get to the center, the more extreme the gravitational gradient becomes. Your feet, slightly closer to the singularity than your head, experience an increasingly stronger pull. The difference in gravitational force between different parts of your body grows larger and larger, until eventually it overcomes the forces that hold your atoms together. But the tidal forces are not the only thing you need to worry about. As you approach the singularity, the curvature of space-time itself becomes more and more extreme. The mathematical description of gravity, Einstein's field equations, begin to predict increasingly bizarre behavior. Time dilation effects that were subtle at the event horizon become dramatic near the center. Distances that seem finite begin to stretch toward infinity. The familiar concepts of measurement and observation break down completely. In a rotating black hole, the situation becomes even more complex and strange. The interior contains not just one singularity, but potentially multiple horizons and regions with different causal structures. There is an inner horizon called the Cauchy horizon, where the curvature of space-time becomes unstable and quantum effects may become important. Beyond this lies the ring singularity, a circle of infinite curvature and density that may have properties unlike anything in the known universe. Some theoretical physicists have speculated that the interior of a rotating black hole might contain regions where the normal flow of causality breaks down, where effect can precede cause, where closed time-like curves make time travel possible. Others have suggested that the ring singularity might be a gateway to other parts of the universe, or even to other universes entirely. These ideas remain highly speculative, but they illustrate just how strange and alien the interior of a black hole can be. The question of what happens to information that falls into a black hole becomes increasingly important as you approach the singularity. According to quantum mechanics, information cannot be destroyed. Every quantum state, every particle property, every bit of data about the arrangement of matter and energy must be preserved in some form. But according to classical general relativity, everything that falls past the event horizon is lost forever, crushed out of existence at the singularity. This creates one of the most profound paradoxes in modern physics. If black holes destroy information, then quantum mechanics is wrong. If information is preserved, then our understanding of black holes must be incomplete. The resolution of this paradox may require a complete revolution in our understanding of space, time, gravity, and the nature of information itself. As you continue your inexorable fall toward the singularity, you become part of this cosmic mystery. Your atoms, your memories, your entire physical existence becomes encoded in the quantum state of the black hole. Whether this information is truly lost or somehow preserved in a form we do not yet understand remains one of the deepest unsolved problems in theoretical physics. The mathematics of general relativity suggests that your journey will end at the singularity, where the curvature of space-time becomes infinite and the density of matter reaches impossible values. But this may be where our current theories simply break down, where the classical description of gravity gives way to something new and unknown. The singularity may not be a place where physics ends, but rather a boundary where new physics begins. What happens when you reach the core, the singularity itself? The answer to this question takes us to the very limits of human knowledge, to the frontier where our best theories encounter their ultimate test, and where the nature of reality itself hangs in the balance. At the heart of every black hole lies something that should not exist, a mathematical impossibility, a point where the equations that govern our universe produce infinities, where the laws of physics as we know them simply cease to function. This is the singularity, and it represents perhaps the greatest challenge to human understanding in all of science. According to general relativity, the singularity is a point of infinite density and zero volume, where all the matter that formed the black hole is compressed beyond any conceivable limit. It is a place where space-time curvature becomes infinite, where the gravitational field strength reaches impossible values, where the very concepts of space and time lose their meaning. But what does it really mean for something to have infinite density? How can we comprehend a point that contains mass but occupies no space? Imagine trying to squeeze all the matter in the Earth into a volume smaller than an atom, then smaller than a proton, then smaller still, until it occupies no space at all while retaining all of its mass. This is what general relativity tells us happens at the center of a black hole. Every kilogram of matter that ever fell past the event horizon, from the original collapsing star to every particle of dust and gas that has been captured over millions or billions of years, all compressed into a single point of infinite density. The mathematics of this situation becomes truly bizarre. When physicists try to calculate the properties of a singularity using the equations of general relativity, they encounter infinities at every turn. The curvature of space-time becomes infinite. The tidal forces become infinite. The gravitational time dilation becomes infinite. These infinities are not just very large numbers, They represent a complete breakdown of the mathematical framework we use to describe reality. In the language of mathematics, we say that the equations become singular at this point. This is not simply a technical difficulty or a computational problem that might be solved with better mathematics or more powerful computers. It represents a fundamental limitation of general relativity itself, a boundary beyond which the theory cannot provide meaningful predictions about the physical world. But singularities are not unique to black holes. They appear throughout physics whenever we push our theories to their ultimate limits. In the standard model of cosmology, the Big Bang itself began with a singularity, a point of infinite density and temperature from which all of space and time emerged. When we try to trace the history of the universe backward to its very beginning, we encounter the same mathematical breakdown, the same infinities that plague our understanding of black holes. The existence of singularities has troubled physicists since the earliest days of general relativity. Einstein himself was uncomfortable with these mathematical pathologies and hoped that some physical mechanism would prevent them from forming in real black holes. He believed that the rotation of collapsing matter, or pressure effects, or quantum mechanical phenomena would somehow halt the collapse before it reached the point of infinite density. For decades, physicists shared Einstein's hope that singularities were merely mathematical artifacts that would disappear when more complete theories were developed. But in the 1960s and 70s, a series of mathematical theorems proved by Roger Penrose and Stephen Hawking showed that singularities are not just possible, but inevitable. Any sufficiently massive object that undergoes gravitational collapse, regardless of its initial shape, rotation, or composition, must eventually form a singularity if general relativity is correct. These singularity theorems, as they came to be known, represent some of the most profound results in mathematical physics. They show that singularities are not special cases or exotic exceptions, but generic features of gravitational collapse. They are as inevitable as the formation of the event horizon itself, built into the very structure of Einstein's equations. The Penrose-Hawking theorems rely on a few key assumptions about the nature of matter and energy. They assume that gravity is always attractive, that energy density is always positive, and that space-time satisfies certain reasonable smoothness conditions. Given these assumptions, the theorems prove that any trapped surface, any region where light rays are converging rather than diverging, must lead inevitably to a singularity in the future. But what exactly is a singularity? Is it a physical object that exists at a specific location in space? Is it an event that occurs at a particular moment in time? Or is it something else entirely? Something that transcends our usual categories of space and time? The answer depends on which type of singularity we are discussing. In a non-rotating black hole, the singularity is space-like, meaning it exists at a specific moment in the future of anything that falls past the event horizon. It is not a place you can visit, but rather a moment in time that you will inevitably experience if you cross the event horizon. All matter that falls into the black hole reaches this singular moment simultaneously, regardless of when it originally crossed the event horizon. But in a rotating black hole, the situation is different and even more strange. The Kerr solution predicts a ring singularity, a circle of infinite curvature and density rather than a point. This ring singularity is time-like rather than space-like, meaning it exists at all times rather than at a specific moment. In principle, you could orbit around this ring, approaching it arbitrarily closely without ever actually reaching it. The ring singularity of a rotating black hole has inspired some of the most speculative ideas in theoretical physics. Some physicists have suggested that the ring might be traversable, that matter and energy could pass through it and emerge in a different region of spacetime. Others have proposed that the ring might be a gateway to other universes, a cosmic wormhole that connects our universe to realms beyond our imagination. These ideas remain highly speculative because they rely on the assumption that general relativity remains valid all the way down to the singularity. But most physicists believe that this assumption is almost certainly wrong. Long before matter reaches the mathematical singularity predicted by general relativity, quantum effects should become important, potentially preventing the formation of true infinities. The scale at which quantum effects become important is set by the Planck length, approximately 10 to the power of minus 35 meters. This is the length scale at which the uncertainty principle of quantum mechanics begins to affect the geometry of space-time itself. At distances smaller than the Planck length, the smooth, continuous space-time of general relativity gives way to a foamy, probabilistic structure where the very concepts of distance and time become uncertain. If quantum effects prevent the formation of true singularities, then what happens at the center of a black hole? This question has motivated decades of research into quantum gravity, the attempt to merge general relativity with quantum mechanics into a single, unified theory of space-time and matter. One possibility is that quantum effects halt the gravitational collapse just before a singularity forms, creating an object of finite but extremely high density. Such an object might be supported by quantum pressure effects, similar to how white dwarf stars are supported by electron degeneracy pressure or neutron stars by neutron degeneracy pressure, but involving even more exotic forms of quantum matter. Another possibility is that the collapse continues, but is regulated by quantum effects that prevent true infinities from forming. The singularity might be replaced by a quantum bounce, where matter reaches a maximum density and then begins to expand again, potentially creating a new universe on the other side of the black hole. Still another possibility is that the concept of a singularity is meaningless, because space and time themselves become quantized at the Planck scale. In theories like loop quantum gravity, space-time is made up of discrete units, like pixels on a computer screen. In such theories, it becomes impossible to compress matter into a point of zero volume, because space itself has a granular structure. The resolution of the singularity problem may require not just new physics, but new ways of thinking about the nature of space, time, and matter. It may force us to abandon some of our most cherished assumptions about the continuity of space-time or the deterministic nature of physical laws. The singularity also raises profound questions about the nature of information and memory. If matter is crushed to infinite density at the singularity, what happens to the information it contained? Are the quantum states that describe the arrangement of atoms and molecules simply destroyed, or are they preserved in some form that we do not yet understand? This question becomes even more pressing when we consider that black holes are not permanent objects. According to Stephen Hawking's calculations, they slowly evaporate through the emission of thermal radiation, eventually disappearing completely. If the information that falls into a black hole is destroyed at the singularity, then this information is lost forever when the black hole evaporates, violating one of the fundamental principles of quantum mechanics. The singularity thus lies at the heart of the information paradox, one of the deepest problems in theoretical physics. The resolution of this paradox may require us to completely rethink our understanding of what happens at the center of a black hole, to abandon the classical picture of a point of infinite density in favor of something far more subtle and strange. Some physicists have proposed that singularities are protected by cosmic censorship, the idea that they are always hidden behind event horizons and can never be observed directly. This would mean that the breakdown of physics at the singularity is hidden from the rest of the universe, preventing paradoxes and inconsistencies from affecting the regions where our theories remain valid. But even if singularities are hidden from direct observation, their existence still poses fundamental challenges to our understanding of the universe. They represent boundaries of knowledge, frontiers beyond which our current theories cannot venture. They are cosmic question marks, challenging us to develop new physics, new mathematics, and new ways of thinking about the deepest mysteries of existence. The singularity remains one of the most profound and challenging concepts in all of science. It represents the ultimate test of our theories, the place where the familiar laws of physics encounter their greatest challenge. Whether singularities actually exist in nature, or whether they are merely artifacts of our incomplete understanding, remains one of the greatest unsolved problems in physics. But do we have to accept that the laws of physics just stop working? The answer to this question has motivated some of the most ambitious theoretical projects in modern science, attempts to go beyond general relativity and develop new theories that can describe what really happens at the heart of a black hole. For nearly a century, physicists have been haunted by the breakdown of general relativity at the singularity. But what if the singularity is not the end of physics, but rather a sign that we need better physics? What if the infinities and mathematical breakdowns are not fundamental features of reality, but symptoms of an incomplete theory? This possibility has driven one of the most ambitious quests in modern science, the search for a theory of quantum gravity. The need for quantum gravity arises from a fundamental incompatibility between our two most successful theories of nature. General relativity describes gravity as the curvature of space-time, a smooth, continuous field that governs the motion of planets and the evolution of the universe. Quantum mechanics describes the other three fundamental forces through discrete particles and probabilistic wave functions, where uncertainty and discontinuity are built into the very fabric of reality. For most practical purposes, this incompatibility does not matter. Gravity is by far the weakest of the fundamental forces, so weak that quantum effects are completely negligible in most gravitational situations. When you drop a ball, you do not need to worry about the quantum mechanical uncertainty in its position. When planets orbit stars, they follow smooth, predictable paths that can be calculated using classical physics. But at the center of a black hole, these two worlds collide. The gravitational field becomes so strong that quantum effects can no longer be ignored, while the curvature of space-time becomes so extreme that the smooth geometry of general relativity breaks down. This is the regime where quantum gravity becomes essential, where neither classical general relativity nor ordinary quantum mechanics can provide a complete description of what happens. The challenge of developing a theory of quantum gravity is immense. It requires unifying two theoretical frameworks that seem fundamentally incompatible, that make different assumptions about the nature of space, time, and causality. General relativity treats space-time as a smooth, continuous manifold that can be curved and stretched. Quantum mechanics suggests that at the smallest scales, everything becomes discrete and probabilistic, including potentially space-time itself. One of the leading candidates for a theory of quantum gravity is loop quantum gravity, developed by physicists like Abhay Ashtekar, Carlo Rovelli, and Lee Smolin beginning in the 1980s. This approach takes the radical step of suggesting that space-time itself is quantized, made up of discrete building blocks at the smallest possible scale. In loop quantum gravity, space is not smooth and continuous, but rather composed of tiny loops and nodes forming a kind of cosmic fabric at the Planck scale. These loops are incredibly small, about 10 to the power of -35 meters across, far smaller than atoms or even atomic nuclei. At this scale, the familiar concepts of distance and area become quantized, coming in discrete units rather than continuous values. The quantization of space in loop quantum gravity has profound implications for black holes and singularities. If space cannot be divided into arbitrarily small pieces, then matter cannot be compressed to infinite density. The collapse of matter toward a singularity would be halted when it reaches the Planck density. roughly 10 to the power of 96 kilograms per cubic meter. At this point, quantum pressure effects would become dominant, potentially causing the matter to bounce back and begin expanding again. This quantum bounce could have extraordinary consequences. Instead of ending in a singularity where physics breaks down, the collapse of matter in a black hole might continue through to the other side, creating what physicists call a quantum bridge or Einstein-Rosen bridge. Matter that falls into a black hole might emerge in a different region of space-time, or even in a completely separate universe. Some loop quantum gravity models suggest that every black hole might be connected to a white hole, a theoretical object that spews matter and energy outward rather than pulling it inward. In this picture, black holes and white holes would be connected by quantum bridges, creating a cosmic recycling system where matter is not destroyed, but merely transported to different regions of the universe. Another leading approach to quantum gravity is string theory, perhaps the most mathematically sophisticated attempt to unify all the fundamental forces of nature. String theory proposes that the most basic constituents of matter are not point particles, but tiny vibrating strings of energy. These strings exist in a higher dimensional space-time, with the extra dimensions curled up so small that they are invisible at everyday scales. In string theory, the properties of particles like mass, charge, and spin are determined by the vibrational patterns of these fundamental strings. Gravity itself emerges from a particular vibrational mode of closed strings, providing a natural way to incorporate gravity into the quantum mechanical framework that describes the other fundamental forces. String theory offers several different scenarios for what might happen at the center of a black hole. In some versions, the singularity is replaced by a complex structure involving higher dimensional branes, membranes that exist in the extra dimensions of string theory. Matter that reaches the center of a black hole might be transformed into exotic, stringy states that have no analog in ordinary physics. One of the most intriguing proposals in string theory is the fuzzball conjecture, developed by Samir Mathur and his collaborators. This idea suggests that black holes are not empty regions of space with singularities at their centers, but rather highly excited quantum states of strings and branes that fill the entire volume inside the event horizon. From the outside, these fuzzballs would look exactly like conventional black holes, but their interiors would be completely different. In the fuzzball picture, there is no singularity and no information paradox. The information that falls into a black hole is not destroyed, but rather encoded in the complex quantum state of the fuzzball. When the black hole eventually evaporates through Hawking radiation, this information is gradually released back to the outside universe, preserving the fundamental principles of quantum mechanics. String theory also predicts the existence of additional types of black holes that have no analog in general relativity. These include black strings, black branes, and even more exotic objects that exist only in higher dimensions. The behavior of these objects could provide crucial insights into the nature of quantum gravity and the fundamental structure of space-time. Another approach to quantum gravity focuses on the holographic principle, the idea that all the information contained in a volume of space can be encoded on its boundary. This principle was inspired by the work of Jacob Bekenstein and Stephen Hawking, who showed that the entropy of a black hole is proportional to the area of its event horizon rather than its volume. The holographic principle suggests that black holes are not three-dimensional objects, but rather two-dimensional holograms projected onto their event horizons. All the information about the matter and energy that falls into a black hole is encoded on the surface of the event horizon, where it can in principle be retrieved when the black hole evaporates. This holographic description of black holes has been given concrete mathematical form through the ADS-CFT correspondence, a remarkable duality discovered in string theory by Juan Maldacena in 1997. ADS-CFT correspondence shows that certain gravitational theories in higher dimensions are equivalent to quantum field theories living on their boundaries, providing a precise mathematical framework for understanding how gravity can emerge from more fundamental quantum mechanical principles. In the ADS-CFT framework, the interior of a black hole corresponds to complex quantum entanglement patterns in the boundary theory. The singularity, if it exists at all, would correspond to a breakdown of these entanglement patterns, possibly signaling the need for new physics beyond the current formulation of ADS-CFT. Causal set theory represents yet another approach to quantum gravity, proposing that spacetime is fundamentally discrete rather than continuous. In this framework, spacetime is composed of discrete events connected by causal relationships, forming a network that approximates smooth spacetime at large scales, but reveals its granular structure at the Planck scale. In causal set theory, black holes would have discrete rather than continuous interiors, with the singularity replaced by a finite number of discrete events. The collapse of matter would proceed through a finite number of steps, each corresponding to a fundamental unit of spacetime, until it reaches a minimal configuration that cannot be further compressed. Emergent gravity theories propose that gravity itself is not a fundamental force, but rather an emergent phenomenon that arises from more basic microscopic physics. These theories, inspired by the work of Eric Verlinde and others, suggest that spacetime and gravity emerge from the entanglement properties of quantum information, much like temperature and pressure emerge from the statistical behavior of molecules in a gas. In emergent gravity scenarios, black holes might be thermodynamic objects whose properties arise from the collective behavior of vast numbers of microscopic quantum degrees of freedom. The singularity would represent a phase transition in this microscopic system, similar to how water turns to steam when heated beyond its boiling point. All of these approaches to quantum gravity remain speculative and incomplete. None has yet produced a fully consistent theory that can make detailed, testable predictions about what happens at the center of a black hole. The mathematical challenges are enormous, requiring new techniques and insights that push the boundaries of theoretical physics. But the quest for quantum gravity is about more than just resolving the singularity problem. It represents an attempt to understand the deepest levels of reality, to discover the fundamental laws that govern the universe at its most basic level. The resolution of the black hole singularity may be just one piece of a much larger puzzle, a puzzle that could revolutionize our understanding of space, time, matter, and information. The stakes could not be higher. If successful, quantum gravity could provide answers to some of the most profound questions in science. What happened at the moment of the Big Bang? Are there other universes beyond our own? What is the ultimate fate of information that falls into black holes? How many dimensions does spacetime really have? These questions have driven theoretical physicists to explore ideas that would have seemed like pure fantasy just a few decades ago. They have led to proposals for parallel universes, extra dimensions, holographic realities, and quantum bridges between different regions of spacetime. Some of these ideas may prove correct, others may be abandoned as our understanding evolves, but all represent serious attempts to grapple with the deepest mysteries of existence. The development of quantum gravity is one of the greatest intellectual challenges of our time, requiring not just new mathematics and new physics, but potentially new ways of thinking about the nature of reality itself. The singularities at the centers of black holes may be the key that unlocks these deeper truths, the cosmic laboratories where the next revolution in physics will be born. But there is another mystery lurking in the depths of black holes, one that challenges not just our understanding of gravity and space-time, but our most basic assumptions about the nature of information and knowledge. What happens to the information that falls into a black hole? And can it ever escape? In 1975, Stephen Hawking made a discovery that would shake the foundations of physics and spark a debate that continues to this day. he showed that black holes are not perfectly black, but instead emit a faint glow of thermal radiation. This Hawking radiation, as it came to be known, meant that black holes could slowly evaporate, gradually returning their mass energy to the universe, one particle at a time. But this discovery created a paradox so profound that it challenged the very foundations of quantum mechanics and our understanding of information itself. To understand the information paradox, we must first understand what physicists mean by information. In the quantum mechanical sense, information refers to the complete specification of a quantum state. All the properties and relationships that determine how a system will behave. When you burn a book, the information contained in the words is not truly destroyed, but rather converted into heat, smoke, and ash. In principle, if you could track every atom and photon produced by the fire, you could reconstruct the original text by running the combustion process in reverse. This principle, that information cannot be truly destroyed, is one of the fundamental tenets of quantum mechanics. It ensures that the universe remains predictable and that the laws of physics work the same way forward and backward in time. If information could be destroyed, then the quantum mechanical evolution of systems would not be reversible, and the fundamental symmetries that underlie our understanding of nature would be broken. But black holes seem to violate this principle in the most dramatic way possible. When matter falls past the event horizon of a black hole, it appears to be lost forever, trapped in a region of space-time from which no information can escape. All the quantum information that specified the arrangement of atoms, the spin of particles, the entanglement relationships between different components, seems to vanish into the interior of the black hole, never to be seen again. The situation becomes even more troubling when we consider Hawking radiation. Hawking showed that quantum effects near the event horizon cause black holes to emit thermal radiation, photons and particles that carry energy away from the black hole. Over time, this process causes the black hole to lose mass and gradually shrink. For stellar mass black holes, this evaporation process is incredibly slow, taking far longer than the current age of the universe to complete. But for smaller black holes, if they exist, the evaporation would be much faster and more dramatic. The problem is that Hawking radiation appears to be completely thermal, meaning it contains no information about what fell into the black hole. Thermal radiation is the most random, most featureless form of energy possible, like the glow from a perfect blackbody radiator. It tells you nothing about the detailed structure of the system that produced it, only its temperature and total energy. This creates an impossible situation. If a black hole forms by the collapse of a massive star, all the information about the arrangement of matter in that star appears to be lost when the black hole eventually evaporates. The Hawking radiation that emerges carries no trace of the original stellar material, no record of how the atoms were arranged, no memory of the quantum states that existed before the collapse. The paradox becomes even more acute when we consider what happens during the final stages of black hole evaporation. As a black hole shrinks, its temperature increases and it radiates more and more rapidly. In the final moments before complete evaporation, the black hole would be incredibly hot and luminous, releasing enormous amounts of energy in a final burst of radiation. But even this spectacular finale would be purely thermal, carrying no information about anything that ever fell into the black hole. Stephen Hawking initially believed that information could indeed be destroyed in black holes, that this was simply a new feature of physics that we would have to accept. He argued that the combination of general relativity and quantum mechanics naturally led to information loss, and that this was not necessarily a problem for physics. Perhaps, he suggested, the fundamental laws of nature allowed for some processes to be truly irreversible. But this suggestion horrified many physicists, particularly those working in quantum field theory and particle physics. Information conservation is so fundamental to quantum mechanics that abandoning it would require rebuilding much of physics from the ground up. It would mean that the universe is not deterministic, that identical initial conditions could lead to different outcomes, that the fundamental symmetries of nature are broken in the most dramatic way possible. The information paradox sparked decades of intense research and debate. Some physicists argued that information is never truly lost, that it must somehow be preserved even when matter falls into black holes. Others accepted Hawking's conclusion that information can be destroyed and worked to understand the implications of this for the rest of physics. Still others suggested that the paradox revealed fundamental flaws in our understanding of black holes, space-time, or quantum mechanics itself. One proposed resolution involves the idea that information is not destroyed at the singularity, but rather encoded on the event horizon itself. According to the holographic principle, all the information that falls into a black hole is stored on its two-dimensional surface, like a cosmic hard drive. When the black hole evaporates, this information could in principle be released back to the outside universe, carried by correlations in the Hawking radiation that are too subtle to detect with current technology. This holographic solution requires that the Hawking radiation is not truly thermal, but rather contains incredibly complex correlations that encode all the information about everything that ever fell into the black hole. The radiation would appear thermal to any observer who could not measure these subtle correlations, but the information would still be there, preserved in the quantum entanglement between different particles in the radiation. The mathematics of this holographic encoding is extraordinarily complex, involving quantum error correction codes that allow information to be preserved even when the physical system storing it undergoes dramatic changes. These codes are similar to those used in quantum computers to protect quantum information from decoherence and noise, but they must work under the extreme conditions near black hole event horizons. Another proposed resolution involves modifications to general relativity itself. Some physicists have suggested that the event horizon of a black hole is not a smooth, empty region, but rather a firewall, a surface of high-energy particles that destroys anything attempting to cross. In firewall models, information is not lost because nothing actually falls into the black hole. Everything is destroyed at the event horizon, and its information content is immediately released back to the outside universe. The firewall hypothesis is controversial because it violates the equivalence principle, one of the fundamental assumptions of general relativity. According to this principle, there should be nothing special about the event horizon from the perspective of someone falling through it. But firewalls would make the event horizon a very special and dangerous place, creating a clear distinction between inside and outside that contradicts the smooth space-time geometry predicted by Einstein's equations. Some physicists have proposed that black holes are not empty regions with singularities at their centers, but rather solid objects made of exotic quantum matter. These black hole stars, or gravastars, would have no event horizons and no singularities, just extremely dense concentrations of matter held together by quantum pressure effects. In such models, information is preserved because nothing ever actually falls into a region of spacetime from which it cannot escape. The fuzzball conjecture from string theory offers another potential resolution. If black holes are really highly excited quantum states of strings and brains that fill their entire interior volume, then information falling into them is not lost but rather becomes part of the complex quantum state of the fuzzball. The apparent loss of information would be an illusion created by our inability to track the incredibly complex quantum dynamics of the fuzzball interior. Recent developments in the study of quantum entanglement have suggested yet another approach to the information paradox. Some physicists now believe that the key to understanding black holes lies not in their gravitational properties, but in their quantum entanglement structure. Black holes may be best understood as complex networks of quantum entanglement, where information is preserved in the correlations between different parts of the system, rather than in any individual components. This entanglement-based approach has led to remarkable discoveries about the relationship between geometry and quantum information. Physicists have found that the connectivity of space-time, the ability to travel from one region to another, is intimately connected to quantum entanglement between those regions. Einstein-Rosen bridges, the theoretical wormholes that might connect black holes to other parts of the universe, may actually be manifestations of quantum entanglement between distant regions of space-time. The famous slogan, "Entanglement equals geometry," captures this deep connection between quantum information and space-time structure. If this relationship is correct, then the information paradox may not be about information falling into black holes and being lost, but rather about information being redistributed through the quantum entanglement network that underlies space-time itself. The resolution of the information paradox remains one of the most important unsolved problems in theoretical physics. It touches on fundamental questions about the nature of space, time, information, and quantum mechanics. The answer may require new physics that goes beyond both general relativity and standard quantum mechanics, a theory of quantum gravity that can properly describe what happens when these two frameworks are pushed to their limits. The stakes of this debate extend far beyond black holes themselves. Information conservation is so fundamental to our understanding of physics that any violation would have profound implications for quantum mechanics, thermodynamics, and our understanding of the universe itself. If information can be destroyed in black holes, what does this mean for the predictability of physical laws? If information is preserved, how can we understand the apparent thermal nature of Hawking radiation? Some physicists believe that resolving the information paradox will lead to a revolution in physics comparable to the development of quantum mechanics or relativity. Others argue that the paradox reveals fundamental limits to what we can know about the universe, boundaries beyond which scientific inquiry cannot venture. The debate has also raised profound philosophical questions about the nature of information itself. Is information a fundamental feature of reality, as basic as matter and energy? Or is it an emergent property that arises from more fundamental physical processes? Can information exist independently of the physical systems that encode it? These questions blur the boundaries between physics and philosophy, challenging our most basic assumptions about the nature of existence. Stephen Hawking himself changed his mind about information loss several times over the course of his career. In 2004, he famously conceded a bet he had made with physicist John Preskill, acknowledging that information is probably not destroyed in black holes after all. But even this concession did not resolve the paradox. It merely shifted the question from whether information is preserved to how it is preserved. The information paradox has become a powerful tool for probing the deepest levels of reality, a cosmic laboratory for testing our most fundamental theories. Black holes may be the key to understanding not just gravity and space-time, but the very nature of information and knowledge itself. The resolution of this paradox may unlock secrets about the universe that we can barely imagine, revealing new connections between quantum mechanics, gravity, information theory, and the fundamental structure of reality. So how does a black hole evaporate, and what happens at the end? The answer to this question may hold the key to resolving the information paradox and understanding the ultimate fate of matter and energy in our universe. Black holes may be the ultimate cosmic prisoners, trapping everything that falls past their event horizons with no possibility of escape. But Stephen Hawking's revolutionary discovery in 1974 revealed something remarkable. These cosmic monsters are not immortal. They are slowly dying, radiating away their mass and energy one quantum at a time, gradually shrinking until they disappear completely from the universe. This process of black hole evaporation is one of the most beautiful and counterintuitive predictions in all of physics, connecting quantum mechanics, thermodynamics, and gravity in ways that continue to surprise and inspire physicists today. The mechanism behind Hawking radiation is rooted in one of the strangest aspects of quantum mechanics, the fact that empty space is not truly empty. According to quantum field theory, The vacuum is filled with virtual particle pairs that constantly pop into existence and annihilate each other in time so short that they cannot be directly observed. These quantum fluctuations are present everywhere in the universe, but they become important near black holes because of the extreme curvature of space-time. Near the event horizon of a black hole, these virtual particle pairs can be separated by the intense gravitational field. One particle falls into the black hole, while the other escapes to infinity, becoming real in the process. To conserve energy, the particle that falls into the black hole must have negative energy relative to distant observers, while the escaping particle carries positive energy away from the black hole. The net result is that the black hole loses mass and energy, while the outside universe gains a stream of particles. This Hawking radiation has several remarkable properties. First, it is thermal, meaning it has the spectrum of radiation emitted by a perfect blackbody at a specific temperature. The temperature of this radiation is inversely proportional to the mass of the black hole, so smaller black holes are hotter than larger ones. A black hole with the mass of our Sun would have a temperature of only about 60 billionths of a Kelvin, far colder than the cosmic microwave background radiation that fills the universe. But a black hole with the mass of a mountain would have a temperature comparable to that of the Sun's surface. And a microscopic black hole with the mass of a large asteroid would be incredibly hot, billions of degrees, radiating primarily in the form of high-energy gamma rays and elementary particles. The relationship between mass and temperature means that as a black hole evaporates and loses mass, it becomes hotter and hotter, radiating more and more rapidly in an accelerating process that leads to its eventual destruction. The timescale for black hole evaporation depends dramatically on the initial mass. The evaporation time is proportional to the cube of the mass, which means that doubling the mass increases the evaporation time by a factor of 8. For a stellar mass black hole with 10 times the mass of our Sun, the evaporation time is approximately 10 to the power of 67 years, a number so large that it defies comprehension. This is far longer than the current age of the universe, longer than the time it will take for all the stars to burn out, longer than the time it will take for protons themselves to decay if current theories are correct. To put this enormous timescale in perspective, imagine that every second since the Big Bang represented a year in the life of a stellar mass black hole. Even then, such a black hole would barely have begun to evaporate by now. The universe would have to exist for a time period longer than the current age, by a factor of 10 to the power of 57 before stellar mass black holes would be noticeably affected by Hawking radiation. Supermassive black holes, the giants that lurk at the centers of galaxies, have even longer lifetimes. A black hole with 1 billion times the mass of our Sun would take approximately 10 to the power of 100 years to evaporate completely. This is a number so large that it exceeds estimates for the lifetime of protons, the decay time of atomic nuclei, and even some estimates for the ultimate fate of space-time itself. But if smaller black holes exist, their evaporation would be much more rapid and dramatic. A black hole with the mass of the Earth would evaporate in about 50 billion years, roughly 10 times the current age of the universe. A black hole with the mass of Mount Everest would last only about 20 billion years. And truly microscopic black holes, if they were somehow created in the early universe or in high-energy particle collisions, could evaporate in fractions of a second. The evaporation process is not uniform throughout the black hole's lifetime. For most of its existence, a black hole radiates very slowly and gently, emitting low-energy photons and a few light particles like electrons and neutrinos. But as the black hole shrinks and its temperature rises, the character of the radiation changes dramatically. In the final stages of evaporation, the black hole becomes incredibly hot and begins to emit all types of particles allowed by the laws of physics. During these final moments, the black hole would radiate not just photons and light particles, but heavy particles like protons, neutrons, and even more exotic forms of matter. If the standard model of particle physics is complete, the black hole would emit all the known elementary particles. But if there are additional particles that we have not yet discovered, particles that are too heavy to create in our current accelerators, these would also be produced in the final stages of black hole evaporation. This makes evaporating black holes potentially powerful tools for exploring physics beyond the standard model. The final burst of radiation from an evaporating black hole could contain signatures of new particles, new forces, or new dimensions of space that are otherwise impossible to detect. Unfortunately, the black holes we observe in the universe are far too massive to evaporate within the lifetime of the universe, so we cannot use them to probe these exotic phenomena. The final moments of black hole evaporation remain one of the greatest mysteries in theoretical physics. What exactly happens when a black hole reaches the end of its life? Does it disappear completely, leaving behind only radiation? Does it leave behind some kind of remnant, a stable or metastable object that preserves some memory of the original black hole? Or does something else entirely happen? Something that we cannot predict with our current understanding of physics. One possibility is that black holes evaporate completely, disappearing entirely and leaving behind only thermal radiation. In this scenario, all the mass and energy of the original black hole is converted into Hawking radiation and dispersed throughout the universe. This would represent the ultimate triumph of quantum mechanics over gravity, the complete dissolution of the most gravitationally bound objects in the universe. But complete evaporation creates serious problems for the information paradox. If black holes disappear entirely, taking with them all information about everything that ever fell into them, then quantum mechanics would be violated in the most fundamental way possible. This possibility is so troubling to many physicists that they have proposed alternatives that preserve information at the cost of abandoning other cherished principles. Another possibility is that black hole evaporation stops before completion, leaving behind a remnant that preserves all the information that fell into the original black hole. These remnants would be incredibly small, possibly at the Planck scale, but they would have enormous internal entropy, capable of storing vast amounts of information in their quantum states. The problem with remnants is that they would have to be able to store arbitrarily large amounts of information in objects of fixed size. This seems to violate basic principles of thermodynamics and statistical mechanics, leading many physicists to reject remnant solutions to the information paradox. If remnants exist, they would have to be governed by physics that is completely different from anything we currently understand. A third possibility is that the final stages of black hole evaporation are governed by quantum gravity effects that dramatically alter the evaporation process. Instead of smooth, continuous evaporation, leading to either complete disappearance or a small remnant, quantum gravity might cause the black hole to undergo a rapid phase transition in its final moments. Some theories suggest that the final burst of radiation from an evaporating black hole could be far more energetic and complex than thermal evaporation would predict. The black hole might release all its remaining mass energy in a single explosive event, a quantum firework that encodes all the information about everything that ever fell into the black hole in the correlations between the emitted particles. Loop quantum gravity suggests yet another possibility. In this framework, the evaporation process might reverse itself before completion, with the black hole undergoing a quantum bounce that transforms it into a white hole. The information that appeared to be lost would then be expelled in a dramatic reversal of the original collapse, creating a cosmic recycling process that preserves information while respecting the principles of quantum mechanics. String theory offers its own set of possibilities for the final fate of evaporating black holes. If black holes are really fuzzballs, complex quantum states of strings and branes, then their evaporation would not involve the emission of thermal radiation from a classical event horizon, but rather the gradual unraveling of an enormously complex quantum system. The final state would not be empty space, but rather a configuration of strings that preserves all the original information in a highly scrambled form. The observational signatures of black hole evaporation remain largely theoretical because of the incredibly long timescales involved. The Hawking radiation from stellar mass and supermassive black holes is far too faint to detect with any conceivable technology. The temperature of the radiation is so low that it is completely swamped by the cosmic microwave background radiation that fills the universe. But if primordial black holes exist, small black holes that formed in the early universe from density fluctuations rather than stellar collapse, some of them might be evaporating today. A primordial black hole with an initial mass comparable to that of a large asteroid would be reaching the end of its life right now, after nearly 14 billion years of evaporation. The final explosion of such a primordial black hole would be detectable as a burst of high-energy gamma rays, a signature that astronomers have been searching for without success. The absence of such bursts places constraints on the population of primordial black holes and provides indirect tests of Hawking's theory of black hole evaporation. Laboratory analogues of black holes, systems that mimic some aspects of event horizons using sound waves in fluids or light in optical media, have provided some experimental confirmation of the basic principles underlying Hawking radiation. These analog systems can be used to test the quantum field theory that predicts thermal radiation from event horizons. Though they cannot probe the full complexity of gravitational physics, the study of black hole evaporation has led to profound insights into the connections between gravity, quantum mechanics, and thermodynamics. Black holes behave like thermodynamic systems with well-defined temperatures and entropies, obeying laws that are remarkably similar to the laws of classical thermodynamics. This has led to the development of black hole thermodynamics, a field that has revealed deep connections between information theory, statistical mechanics, and quantum gravity. The evaporation of black holes also raises profound questions about the ultimate fate of the universe itself. In the far future, when all the stars have burned out and all ordinary matter has decayed or been consumed by black holes, the evaporation of black holes through Hawking radiation may be the last source of energy in the universe. The final black holes would serve as cosmic heat engines, slowly converting their mass into radiation and providing the last flickering light in an otherwise cold and empty cosmos. But even this process would eventually come to an end. When the last black hole evaporates, the universe would enter its final phase, a state of maximum entropy where no further work can be extracted from any physical system. This heat death of the universe represents the ultimate triumph of the second law of thermodynamics, the final victory of entropy over order. Yet, even this seemingly final conclusion remains uncertain. The evaporation of black holes might not represent the end of interesting physics, but rather a transition to new forms of cosmic evolution governed by quantum gravity effects that we do not yet understand. The universe might undergo cycles of expansion and contraction, or spawn new universes through quantum tunneling events, or evolve in ways that are completely beyond our current imagination. The death of black holes thus connects to some of the deepest questions in cosmology and fundamental physics. But their evaporation also raises another profound mystery. What if a black hole does not simply destroy the information that falls into it, but rather moves it somewhere else, encoding it in ways that transcend our usual understanding of space and time? What if everything we think we know about black holes is wrong? What if the event horizon is not an invisible boundary that you can cross unharmed, but a wall of fire that incinerates anything that approaches? What if the interior of a black hole is not a region of curved space-time leading to a singularity, but a bridge to other parts of the universe or even other universes entirely. These radical possibilities have emerged from decades of research into the quantum properties of black holes, leading to ideas so strange and counterintuitive that they challenge our most basic assumptions about space, time, and reality itself. The story begins with one of the most famous equations in physics, Einstein's field equation from general relativity, which has a peculiar mathematical property. For every solution that describes matter collapsing inward to form a black hole, there exists another solution that describes matter exploding outward from what physicists call a white hole. These white holes would be the exact opposite of black holes, regions of space-time that spew matter and energy outward, from which nothing can enter, rather than regions from which nothing can escape. White holes have never been observed in nature, and most physicists believe they cannot exist as isolated objects because they would be fundamentally unstable. Any small perturbation, any tiny amount of matter trying to fall into a white hole would cause it to collapse and disappear. But in 1935, Einstein and his colleague Nathan Rosen discovered something remarkable. The mathematical solution that describes a black hole could be extended through the singularity to reveal a white hole on the other side, connected by a bridge through spacetime. This Einstein-Rosen bridge, as it came to be known, represents one of the most exotic predictions of general relativity. It suggests that every black hole might be connected to a white hole somewhere else in the universe, or even in another universe entirely. Matter that falls into the black hole would travel through this cosmic tunnel and emerge from the white hole, creating a kind of cosmic recycling system that preserves information and energy while transporting it across vast distances of space and time. The Einstein-Rosen bridge is more commonly known today as a wormhole, a term coined by physicist John Wheeler to capture the idea of a tunnel that connects distant regions of space-time, like a worm tunnel through an apple. But there is a fundamental problem with these classical wormholes. According to general relativity, they are unstable and would collapse so quickly that nothing, not even light, could travel through them from one end to the other. For decades, wormholes remained a mathematical curiosity, solutions to Einstein's equations that seemed to have no relevance to the real universe. But in recent years, advances in our understanding of quantum mechanics and black hole physics have suggested that wormholes might be more than just abstract mathematical constructs. They might be fundamental features of space-time that play a crucial role in resolving some of the deepest paradoxes in physics. The key insight came from studying quantum entanglement, one of the strangest phenomena in quantum mechanics. When two particles become entangled, their quantum states become correlated in such a way that measuring one particle instantly affects the other, regardless of the distance between them. Einstein famously called this spooky action at a distance, and it troubled him deeply because it seemed to violate the principle that nothing can travel faster than light. But entanglement is not just a strange quantum phenomenon, it is a fundamental feature of how information is stored and processed in quantum systems. When particles become entangled, they share information in ways that cannot be described by classical physics. The total information content of the system becomes encoded not in the individual particles, but in the correlations between them. In 2013, physicists Juan Maldacena and Leonard Susskind proposed a revolutionary idea that connected quantum entanglement to the geometry of space-time itself. They suggested that Einstein-Rosen bridges and quantum entanglement are actually the same phenomenon viewed from different perspectives. In their formulation, which they called ER equals EPR after Einstein-Rosen bridges, and the Einstein-Podolsky-Rosen paradox that first highlighted the strangeness of entanglement, wormholes are the geometric manifestation of quantum entanglement. This ER equals EPR correspondence suggests that when two black holes become quantum entangled, they are connected by a wormhole through spacetime. The entanglement between the black holes stabilizes the wormhole, preventing it from collapsing and making it traversable, at least in principle. Information that falls into one black hole could travel through the wormhole and emerge from the other, preserving the total information content of the system while allowing it to be redistributed across space and time. The implications of this idea are staggering. If ER equals EPR is correct, then the universe is laced with wormholes connecting every pair of entangled particles. These quantum wormholes would be incredibly tiny, much smaller than atomic nuclei, but they would form a vast network that underlies the apparent separateness of space and time. The connectedness of quantum entanglement would be revealed as a literal connectedness through higher dimensional wormhole bridges. But the story becomes even stranger when we consider what happens to these wormholes as black holes evaporate through Hawking radiation. As a black hole emits radiation and shrinks, its entanglement with the outside universe grows stronger and stronger. According to ER equals EPR, this means that the wormhole connecting the black hole to its radiation becomes longer and longer, stretching across vast distances as the entanglement spreads throughout the universe. This picture suggests a radical reinterpretation of black hole evaporation. Instead of thermal radiation being emitted from the event horizon and carrying no information about the black hole's interior, the radiation would be connected to the black hole through microscopic wormholes that preserve all the information while making it appear scrambled and inaccessible to local observers. But this elegant resolution of the information paradox faces a serious challenge known as the firewall paradox. In 2012, physicists Ahmed Almhairi, Donald Marolf, Joseph Polchinski, and James Sully pointed out a fundamental conflict between different requirements for black hole physics. They showed that you cannot simultaneously preserve the equivalence principle, which says that falling into a black hole should feel no different from floating in empty space, maintain the unitarity of quantum mechanics, which requires information conservation, and accept that Hawking radiation is thermal from the perspective of outside observers. The firewall argument suggests that something has to give, and the most radical possibility is that the event horizon is not empty space, but rather a firewall, a region of space filled with high-energy particles that would incinerate anything attempting to cross. The firewall would form because the quantum entanglement structure near the event horizon becomes so complex and chaotic that it breaks down, creating a breakdown in the smooth geometry of space-time itself. The firewall hypothesis is deeply troubling to many physicists because it violates one of the most cherished principles of general relativity. The equivalence principle is not just a technical assumption, but a fundamental insight about the nature of gravity and space-time. If firewalls exist, then event horizons become physical barriers rather than mere coordinate artifacts, and the smooth, continuous nature of space-time is broken in the most dramatic way possible. Some physicists have proposed alternatives to firewalls that preserve the equivalence principle while still resolving the information paradox. These include the idea that the interior of black holes is much more complex than general relativity suggests, filled with highly entangled quantum fields that encode information in non-local ways. In such models, information is preserved not by being stored in any particular location, but by being distributed across the entire quantum state of the system. The holographic principle offers yet another perspective on these puzzles. This principle, which emerged from the study of black hole thermodynamics, suggests that all the information contained in a volume of space can be encoded on its boundary. For black holes, this means that everything that falls past the event horizon is actually encoded on the surface of the horizon itself, like a cosmic hologram projected onto a two-dimensional screen. The holographic principle has been given concrete mathematical form through the ADS-CFT correspondence, a remarkable duality discovered in string theory. ADS-CFT shows that certain gravitational theories in higher dimensional curved spacetimes are exactly equivalent to quantum field theories living on their lower dimensional boundaries. This correspondence provides a precise mathematical framework for understanding how gravity and spacetime can emerge from more fundamental quantum mechanical principles. In the ADS-CFT framework, black holes in the higher dimensional bulk spacetime correspond to thermal states in the lower dimensional boundary theory. The evaporation of the black hole corresponds to the relaxation of this thermal state back to its ground state, a process that is perfectly unitary and preserves all information. The apparent loss of information in the bulk theory is revealed to be an illusion created by our inability to access the complete boundary description. The holographic description of black holes suggests that the interior of a black hole may not exist as an independent region of spacetime, but rather as an emergent phenomenon that arises from the complex quantum entanglement structure of the boundary theory. In this view, the question of what happens inside a black hole becomes a question about the organization of quantum information in strongly correlated systems. Recent developments in holographic duality have led to even more radical ideas about the nature of spacetime itself. Some physicists now believe that space and time are not fundamental features of reality, but rather emergent properties that arise from the entanglement structure of quantum information. In this picture, the geometry of spacetime is determined by how quantum information is distributed and connected throughout the system. This emergence of spacetime from entanglement has profound implications for our understanding of black holes. If spacetime itself is emergent, then the singularities at the centers of black holes may not represent breakdowns of physics, but rather phase transitions in the underlying quantum information structure. The singularity might be a point where the emergent description of spacetime becomes inadequate, requiring a more fundamental description in terms of quantum information. The holographic principle also suggests new ways of thinking about the relationship between black holes and their surroundings. Instead of viewing black holes as isolated objects embedded in spacetime, holography suggests that they are better understood as aspects of the global quantum state of the universe. The information that appears to fall into black holes may never actually leave the boundary of spacetime, but rather becomes encoded in increasingly complex patterns of entanglement. These ideas have led to proposals for holographic models of black hole interiors that preserve information while maintaining the equivalence principle. In these models, the interior of a black hole is not a separate region of spacetime, but rather a shadow or projection of the quantum information encoded on the boundary. Observers falling into the black hole would experience a fully consistent interior spacetime, but this interior would be emergent rather than fundamental. The development of these holographic models has been aided by advances in quantum error correction, the theory of how quantum information can be protected from noise and decoherence. Black holes may function as quantum error, correcting codes that preserve information even when the physical systems storing it undergo dramatic changes. The Hawking radiation would then be analogous to syndrome measurements in a quantum error correcting code, revealing information about errors without destroying the encoded quantum information. All of these ideas remain highly speculative and are still being actively developed by theorists around the world. They represent attempts to reconcile the fundamental principles of quantum mechanics and general relativity in the extreme environment of black holes, where both theories are pushed to their absolute limits. The resolution of these puzzles may require not just new mathematics, but new ways of thinking about the nature of information, space, time, and reality itself. The debate over firewalls, wormholes, and holography has revealed deep connections between seemingly unrelated areas of physics, from quantum information theory to string theory to condensed matter physics. These connections suggest that the ultimate understanding of black holes may come not from studying gravity in isolation, but from understanding how gravity emerges from more fundamental quantum mechanical principles. But perhaps the most radical possibility of all is that black holes are not just cosmic monsters that trap and destroy matter and energy, but rather cosmic creators that give birth to new regions of space-time, new universes, new realities that exist beyond our current understanding of space and time. What if the death of a star is not the end but the beginning? What if every black hole that forms in our universe gives birth to an entirely new cosmos, complete with its own space, time, matter, and perhaps even its own laws of physics? This extraordinary possibility has emerged from some of the most speculative and ambitious theories in modern cosmology, suggesting that our universe might be just one bubble in an infinite cosmic foam, with new universes being born inside black holes throughout space and time. The idea that black holes might be cosmic wombs traces its origins to some peculiar features of Einstein's equations and the strange geometry of space-time near singularities. When physicists first began to understand the mathematical structure of black holes, they discovered that the equations of general relativity allow for solutions far more exotic than simple stellar collapse. These solutions hint at the possibility that the singularity at the center of a black hole might not be the end of space-time, but rather a doorway to something entirely new. One of the most intriguing possibilities emerges from the mathematics of rotating black holes. The Kerr solution, which describes a spinning black hole, predicts that the singularity is not a point, but a ring. This ring singularity has properties unlike anything else in physics, including regions where the normal flow of time breaks down and closed time-like curves become possible. Some physicists have speculated that this ring might be more than just a mathematical curiosity, that it might represent a portal through which matter and energy could pass into a completely different region of space-time. The concept gained scientific respectability through the work of physicists like Lee Smolin, who developed the idea of cosmological natural selection. Smolin proposed that universes reproduce through black holes, with each black hole giving birth to a new universe with slightly different physical constants. Over cosmic time, this process would lead to the evolution of universes, with those that are most efficient at producing black holes becoming more common in the infinite multiverse. In Smolin's model, the parameters that govern physics in our universe, things like the strength of gravity, the mass of electrons, and the rate of cosmic expansion, are not arbitrary constants, but rather the result of a cosmic evolutionary process. Universes that produce many black holes would have many offspring, while universes that produce few black holes would have few descendants. Over countless generations, the multiverse would become dominated by universes that are optimally tuned for black hole production. This idea provides a potential explanation for one of the greatest mysteries in cosmology: the apparent fine-tuning of physical constants for the existence of stars, planets, and life. Instead of requiring some cosmic designer or infinite multiverse of random possibilities, cosmological natural selection suggests that our universe's properties are the result of a selection process that favors universes capable of producing complexity and structure. But the mechanism by which black holes might give birth to new universes remained unclear until the development of theories that combine general relativity with quantum mechanics. One of the most promising approaches comes from loop quantum gravity, which suggests that the singularities predicted by classical general relativity are replaced by quantum bounces when quantum effects are taken into account. In loop quantum gravity, space-time itself is quantized into discrete units at the Planck scale. This quantization prevents matter from being compressed to infinite density, instead causing it to reach a maximum density and then bounce back. For black holes, this quantum bounce might occur not outward into our universe, where it would be trapped behind the event horizon, but rather into a new region of space-time, creating a baby universe that pinches off from our own. The mathematical details of this process are extraordinarily complex, involving the quantum geometry of space-time and the behavior of matter under conditions that push the laws of physics to their absolute limits. But the basic picture is surprisingly elegant. Matter falling into a black hole reaches the quantum bounce point and begins expanding again. But this expansion occurs in a new region of space-time that is causally disconnected from our universe. From the perspective of observers in our universe, the black hole appears to behave normally, with matter falling past the event horizon and disappearing from view. But on the other side of the quantum bounce, the same matter begins the expansion phase of a new Big Bang, creating space, time, and the conditions necessary for the formation of stars, galaxies, and perhaps even life. This scenario suggests that our own universe might have been born inside a black hole in some parent universe. The Big Bang that created our cosmos might not have been the beginning of everything, but rather a quantum bounce inside a black hole formed by the collapse of a massive star in another reality. Our entire observable universe, with its hundreds of billions of galaxies and countless stars and planets, might exist within the event horizon of a black hole in a higher dimensional space. The implications of this idea are staggering. If black holes give birth to new universes, then the cosmos becomes a vast, interconnected network of realities, each spawning countless others in an endless process of cosmic reproduction. The number of universes in this multiverse would be truly infinite, limited only by the number of black holes that have ever formed throughout all of space and time. Each baby universe would inherit the physical laws of its parent, but with small random variations introduced by quantum fluctuations during the bounce process. Over many generations, these small changes would accumulate, leading to the evolution of physical laws and the emergence of universes with properties unlike anything we can imagine. Some baby universes might have stronger gravity, leading to the rapid formation of black holes and a short-lived cosmos dominated by these exotic objects. Others might have weaker gravity, resulting in a universe where stars never form and the cosmos remains a cold, dark sea of elementary particles. Still others might have entirely different forces or particles, creating realities governed by physics that would be completely alien to us. The theory also suggests that our universe is actively reproducing right now. Every stellar mass black hole in our galaxy, every supermassive black hole at the center of distant galaxies, might be in the process of giving birth to new universes. The Milky Way alone contains millions of stellar mass black holes, each potentially creating a new cosmos complete with its own space, time, and physical laws. But the baby universe hypothesis faces significant challenges and criticisms. One of the most serious problems is that it is extremely difficult, perhaps impossible, to test experimentally. By definition, baby universes are causally disconnected from our own, meaning that no information can travel between them. We cannot observe these other universes directly, nor can we influence them or receive signals from them. This makes the theory scientifically problematic because it makes predictions that cannot be verified or falsified through observation or experiment. Some philosophers of science argue that untestable theories are not really science at all, but rather metaphysics or speculation dressed up in mathematical formalism. However, proponents of the baby universe hypothesis point out that the theory does make some testable predictions about our own universe. If cosmological natural selection is correct, then our universe should be nearly optimal for black hole production, with physical constants tuned to maximize the formation of stars massive enough to collapse into black holes. Some studies have suggested that small changes to fundamental constants would indeed dramatically reduce the number of black holes formed, providing indirect support for the theory. The baby universe scenario also faces challenges from our understanding of thermodynamics and information theory. If black holes give birth to new universes, what happens to the information that falls into them? Is it transferred to the baby universe, or is it lost in the process? The resolution of this question may depend on details of quantum gravity, that are still being worked out by theoretical physicists. Another challenge comes from the scale problem. The observable universe contains approximately 10 to the power of 80 atoms, but the interior of a stellar mass black hole would seem to have far too little space to accommodate such a vast amount of matter and energy. How can something smaller than a city give birth to something larger than the observable universe? The answer may lie in the strange properties of space-time geometry near quantum bounces. In theories like loop quantum gravity, the expansion of the baby universe does not occur within the confines of the parent black hole, but rather in a new region of space-time that is created by the bounce itself. The baby universe has its own space and time, not embedded within our universe, but connected to it only through the quantum bounce event. Recent developments in string theory have suggested alternative mechanisms by which black holes might spawn new realities. In some string models, black holes are not simple regions of curved spacetime, but rather complex objects made of extended structures called branes. These branes can interact in ways that create new spatial dimensions or new regions of spacetime, potentially giving rise to bubble universes that inflate from quantum fluctuations in the higher dimensional space. The eternal inflation scenario, developed by physicists like Alan Guth and Andre Linde, suggests that our universe is just one bubble in an eternally inflating multiverse where new regions of space are constantly being created through quantum fluctuations in inflating fields. In some versions of this theory, black holes might serve as nucleation sites for new inflationary bubbles, creating baby universes through a mechanism quite different from the quantum bounce scenario. Other theories propose that black holes might create new universes through wormhole formation. If ER equals EPR is correct, and entanglement creates wormhole connections, then the complex entanglement structure of an evaporating black hole might spawn wormhole networks that grow into new regions of space-time. These wormhole babies would be connected to our universe through quantum entanglement, but would evolve independently, potentially developing their own laws of physics through symmetry-breaking mechanisms. The possibility that our universe was born inside a black hole also raises fascinating questions about the nature of time and causality. If our Big Bang was really a quantum bounce inside a black hole, then our entire cosmic history, from the first moments after the bounce to the formation of galaxies to the evolution of life on Earth, might be taking place within the interior of a black hole in some parent universe. This leads to strange temporal paradoxes. From the perspective of observers in the parent universe, anything that falls into a black hole appears to freeze at the event horizon due to gravitational time dilation. But from our perspective inside the baby universe, billions of years of cosmic evolution have already taken place. These different perspectives on time create puzzles that may require new understanding of the relationship between time, gravity, and quantum mechanics. The baby universe hypothesis also connects to broader questions about the ultimate fate of our cosmos. If our universe was born inside a black hole, what happens when that parent black hole evaporates through Hawking radiation? Does our universe disappear along with it? Or does the baby universe survive independently of its parent? Some theories suggest that baby universes become truly independent once they are created, existing in their own space and time, regardless of what happens to the parent black hole. Others propose that there might be subtle connections that persist, potentially allowing information to flow between parent and child universes in ways that we do not yet understand. The implications extend beyond cosmology to questions about consciousness, meaning, and our place in the universe. If we live inside a black hole in another universe, and if our universe is giving birth to countless others, then we are part of an infinite cosmic family tree, stretching across dimensions of space and time that we can barely comprehend. Some believe black holes don't just destroy, they may create. The possibility that every black hole gives birth to a new universe transforms these objects from cosmic destroyers into cosmic creators. the engines of an infinite multiverse where every collapse leads to a new beginning, every ending becomes a new start, and death becomes the ultimate act of creation. So what do we really know, and what remains a mystery? After exploring the depths of black holes, from their formation to their potential role as cosmic creators, we must now step back and ask what science can actually tell us about what happens inside these enigmatic objects. After journeying through the theoretical landscapes of curved space-time, quantum mechanics, and exotic physics, we arrive at the fundamental question that began our exploration. What actually happens inside a black hole? What can science tell us with confidence, and where do the boundaries of our knowledge lie? The answer is both humbling and extraordinary, revealing the limits of human understanding while pointing toward revolutionary discoveries that may reshape our conception of reality itself. Let us begin with what we know with reasonable certainty, the predictions that emerge from well-tested theories and have withstood decades of scrutiny from the world's most brilliant physicists. When you cross the event horizon of a black hole, particularly a supermassive one, you initially experience nothing unusual. There is no wall, no barrier, no sudden change in the forces acting on your body. The event horizon is not a physical surface, but a geometric boundary in space-time, as invisible and intangible as the equator on Earth. But crossing this boundary changes everything in the most fundamental way possible. Inside the event horizon, the geometry of space-time becomes so warped that the radial direction, the direction pointing toward the center, becomes time-like rather than space-like. This means that moving toward the center becomes as inevitable as moving forward through time. Just as you cannot choose to stop aging or move backward in time, inside a black hole, you cannot choose to stop falling inward. This inversion of space and time creates a region where all possible futures lead to the same destination. Every trajectory, every possible path through space-time converges on the center of the black hole. No force, no technology, no clever trick can alter this fate. It is written into the geometry of space-time itself, as fundamental and inescapable as the laws of mathematics. As you fall deeper into the black hole, tidal forces begin to take their toll. These forces arise because different parts of your body experience slightly different gravitational fields, with your feet feeling a stronger pull than your head if you are falling feet first. For stellar mass black holes, these tidal forces become lethal long before you reach the center, stretching your body like taffy in a process scientists have dubbed spaghettification. But for supermassive black holes, the story is different. Their event horizons are so large that the tidal forces at the boundary are quite gentle. You could cross into the interior of a supermassive black hole and survive for hours or even days, experiencing a relatively peaceful journey through increasingly curved space-time before the tidal forces finally become overwhelming. The exact nature of your final destination remains one of the greatest mysteries in physics. According to general relativity, all matter that falls into a black hole is crushed to infinite density at a mathematical point called the singularity. But this prediction almost certainly breaks down before infinite densities are reached. Long before you encounter the classical singularity predicted by Einstein's equations, quantum effects should become important, potentially preventing the formation of true infinities. What happens in this realm, where quantum mechanics and gravity meet, remains largely unknown. We have candidate theories like loop quantum gravity, string theory, and emergent gravity, each suggesting different possibilities for what might replace the classical singularity. But none of these theories is complete or confirmed, and the physics of quantum gravity remains one of the greatest unsolved problems in science. One possibility is that quantum effects halt the collapse just before a singularity forms, creating a region of finite but extremely high density. Another is that the matter undergoes a quantum bounce, beginning to expand again and potentially creating a new region of space-time or even a new universe. Still another possibility is that the concept of a singularity becomes meaningless because space and time themselves become quantized at the smallest scales. The question of what happens to information that falls into black holes has become one of the most important problems in theoretical physics. According to quantum mechanics, information cannot be destroyed, but according to classical black hole physics, information that crosses the event horizon appears to be lost forever. This information paradox has driven decades of research and led to radical new ideas about the nature of space, time, and information itself. The holographic principle suggests that all information that appears to fall into a black hole is actually encoded on its two-dimensional surface, like a cosmic hologram. In this view, the three-dimensional interior of the black hole might be an illusion, an emergent phenomenon that arises from the complex information processing occurring on the event horizon. Recent developments in our understanding of quantum entanglement have suggested even more radical possibilities. Some physicists now believe that black holes are best understood not as objects embedded in space-time, but as complex networks of quantum information. The Einstein-Rosen bridge connecting black holes to other regions of space-time might be a manifestation of quantum entanglement, suggesting that the geometry of space itself emerges from the entanglement structure of quantum information. These ideas remain highly speculative, but they point toward a revolutionary new understanding of space and time. If space-time itself is emergent from quantum information, then black holes might be windows into the fundamental nature of reality, revealing the quantum informational substrate from which our familiar world emerges. The evaporation of black holes through Hawking radiation adds another layer of complexity to our understanding. Stephen Hawking showed that quantum effects near the event horizon cause black holes to emit thermal radiation, slowly losing mass and energy over time. For stellar mass black holes, this process takes far longer than the current age of the universe. But for smaller black holes, if they exist, evaporation would be much more rapid. The final stages of black hole evaporation remain deeply mysterious. Does the black hole disappear completely, leaving behind only radiation? Does it leave a remnant that preserves information about everything that ever fell into it? Or does something else entirely happen? Something that requires new physics beyond our current understanding? The answers to these questions may depend on physics that operates at energy scales and length scales far beyond anything we can currently probe experimentally. The Planck scale, where quantum effects on space-time geometry become important, is 20 orders of magnitude smaller than the scale of atomic nuclei. The energies required to create microscopic black holes in laboratory conditions are far beyond the reach of any conceivable particle accelerator. This means that much of our understanding of black hole interiors must remain theoretical, based on mathematical consistency and indirect observational evidence, rather than direct experimental verification. We can observe the effects that black holes have on their surroundings, the way they bend light and trap matter, the radiation they emit, and the gravitational waves they produce when they merge. But the interior itself remains hidden behind the event horizon, protected by what physicists call cosmic censorship. Yet this hiddenness does not mean that the study of black holes is purely academic. These objects serve as natural laboratories for testing our most fundamental theories under the most extreme conditions imaginable. They probe the connections between gravity and quantum mechanics, between information and geometry, between the microscopic and the cosmic. Every advance in our understanding of black holes brings us closer to a unified theory of quantum gravity and a deeper understanding of the nature of space, time, and reality. The observational evidence for black holes has grown stronger with each passing year. We have detected gravitational waves from merging black holes, providing direct confirmation of some of general relativity's most exotic predictions. We have imaged the event horizons of supermassive black holes, revealing the shadow cast by these invisible objects against the glowing matter around them. We have tracked stars orbiting the supermassive black hole at the center of our galaxy, confirming the predictions of general relativity in strong gravitational fields. But perhaps most importantly, black holes have taught us about the limits of knowledge and the importance of theoretical physics in pushing beyond those limits. They have shown us that the universe is far stranger and more wonderful than our everyday experience suggests, that space and time are not fixed backdrops for physical processes, but dynamic participants in the cosmic drama. The study of black holes has also revealed deep connections between seemingly unrelated areas of physics. Thermodynamics and gravity, quantum mechanics and geometry, information theory and cosmology all come together in the physics of black holes. These connections suggest that there are fundamental unifying principles underlying all of physics, principles that we are only beginning to understand. Looking toward the future, new observations and new theoretical developments promise to deepen our understanding of these enigmatic objects. Next-generation gravitational wave detectors will allow us to study black hole mergers with unprecedented precision. Advanced telescopes will probe the environments around black holes in ever greater detail. And theoretical physicists continue to develop new mathematical tools and conceptual frameworks for understanding quantum gravity. The question of what happens inside a black hole thus remains partially unanswered, not because of any failure of science, but because we are probing the very foundations of physical reality. Black holes exist at the intersection of our two most successful theories, general relativity and quantum mechanics, in a regime where both theories are pushed to their absolute limits. The resolution of the mysteries surrounding black hole interiors may require a complete revolution in our understanding of space, time, matter, and information. This revolution, when it comes, will likely be as profound as the development of quantum mechanics or relativity, opening up entirely new ways of thinking about the universe and our place within it. In the meantime, black holes continue to challenge us, to inspire us, and to remind us of how much we still do not know about the cosmos we inhabit. They are cosmic question marks, written in the language of curved spacetime and quantum mechanics, asking us to push beyond the comfortable boundaries of established knowledge and venture into the unknown. What we can say with confidence is that inside the event horizon, space becomes time, all paths lead inward, and the familiar rules of physics encounter their ultimate test. At the core, our current physics fails, and we need quantum gravity to know more. Hawking radiation means black holes do not last forever, slowly returning their mass energy to the universe through quantum processes we are only beginning to understand. Information might be preserved, encoded on the horizon through holographic mechanisms, or released in the subtle correlations of late-time radiation. The singularity may not be a point where physics ends, but rather a boundary where new physics begins, where the quantum nature of space-time itself becomes manifest. In the end, black holes may teach us what space and time really are, revealing them not as fundamental features of reality, but as emergent properties of something deeper and more fundamental. They may show us that information and geometry are two aspects of the same underlying reality, that the universe is fundamentally quantum mechanical, even at the largest scales. The journey into a black hole is thus not just a journey through curved space-time, but a journey to the very foundations of existence, to the place where physics meets philosophy and science encounters mystery. It is a reminder that the universe is not only stranger than we suppose, but stranger than we can suppose, full of wonders that challenge our deepest assumptions about the nature of reality itself. What happens in a black hole? After our journey through the deepest mysteries of physics, through the warped geometry of space-time, and the strange realm of quantum mechanics, through speculative theories and established science, we arrive at a profound and humbling conclusion. Maybe everything, maybe nothing. Maybe the blueprint of reality itself is folded inside these cosmic enigmas, waiting to be decoded by future generations of scientists and philosophers. We began this exploration with a simple question, but we have discovered that black holes are anything but simple. They are cosmic laboratories where the most fundamental laws of physics are tested under the most extreme conditions imaginable. They are gateways to questions that challenge our deepest assumptions about space, time, matter, information, and the very nature of existence itself. In our journey, we have seen how black holes emerge from the death of massive stars, how they warp space-time so severely that the familiar concepts of space and time exchange roles, how they trap light itself in their gravitational embrace. We have explored the paradoxes they create, the way they seem to violate the conservation of information while simultaneously teaching us about the deep connections between entropy, thermodynamics, and gravity. We have witnessed the breakdown of our most successful theories at the singularities that lurk at their centers, where the mathematics of general relativity produces infinities, and the smooth geometry of space-time encounters its ultimate limit. We have seen how this breakdown has inspired some of the most ambitious theoretical projects in the history of science, attempts to merge quantum mechanics and gravity into a unified description of nature. Black holes have shown us that the universe is fundamentally quantum mechanical, even at the largest scales. Through Hawking radiation, they reveal that the vacuum of space is alive with quantum fluctuations, that nothing in the universe is truly permanent, that even the most gravitationally bound objects slowly evaporate back into the quantum foam from which they emerged. They have taught us about the holographic nature of information, the possibility that three-dimensional reality might be encoded on two-dimensional surfaces, that the interior of space might be an emergent illusion arising from quantum entanglement on the boundary. They have suggested that space-time itself might not be fundamental, but rather a macroscopic approximation to something deeper and more strange. Through the study of black holes, we have glimpsed the possibility of cosmic recycling, where matter and energy are not destroyed, but transformed and transported to new regions of space-time or even new universes entirely. We have considered the idea that our own universe might have been born inside a black hole, that we might be living within the event horizon of some unimaginably large parent black hole in a higher dimensional space. These ideas push the boundaries of science into territory that borders on philosophy and metaphysics. They force us to confront questions about the nature of reality that humans have pondered for millennia. What is space? What is time? What is information? What is existence itself? Black holes do not provide easy answers to these questions, but they do provide a cosmic context in which to ask them. The mathematics of black holes has revealed deep connections between seemingly unrelated areas of physics. Thermodynamics and gravity, quantum mechanics and geometry, information theory and cosmology all come together in ways that suggest underlying unifying principles that we are only beginning to understand. These connections hint at a more fundamental theory, a theory of quantum gravity that would represent the next great revolution in our understanding of nature. But perhaps most importantly, black holes have taught us about the limits of knowledge and the importance of theoretical exploration beyond those limits. They exist in regimes where direct experimental investigation is impossible, where we must rely on mathematical consistency, theoretical beauty, and indirect observational evidence to distinguish between competing ideas about the nature of reality. This does not make the study of black holes less scientific, but rather reveals science at its most ambitious and creative. When pushed to the boundaries of the known, science becomes an act of imagination, disciplined by mathematics, a way of exploring possibilities that transcend our everyday experience while remaining grounded in logical consistency and empirical evidence. The story of black holes is far from over. New observations continue to reveal their properties and behaviors in ever greater detail. Gravitational wave astronomy has opened an entirely new window into the universe, allowing us to witness the collisions and mergers of black holes in real time. Advanced telescopes are probing the environments around black holes with unprecedented resolution, revealing the complex interplay between these objects and the galaxies that host them. On the theoretical front, the development of quantum gravity continues at an accelerating pace. String theory, loop quantum gravity, emergent gravity, and other approaches are producing new insights into the quantum nature of space-time and the resolution of singularities. The connections between quantum entanglement and geometry are being explored with increasing mathematical precision, potentially leading to a complete reformulation of our understanding of space, time, and gravity. But beyond their scientific importance, black holes have captured the human imagination in ways that few other cosmic phenomena can match. They represent the ultimate unknown, the ultimate challenge to human understanding, the ultimate frontier of exploration. They are cosmic dragons guarding the deepest secrets of the universe, daring us to venture into realms where our familiar intuitions break down and new forms of understanding must be forged. They remind us that the universe is not only more strange than we know, but more strange than we can know, at least with our current theories and conceptual frameworks. They challenge us to think beyond the limitations of our everyday experience, to imagine realities that transcend the familiar categories of space, time, matter, and energy. In contemplating black holes, we are forced to confront our own limitations as conscious beings embedded in a small corner of a vast and mysterious cosmos. We are reminded that science is not just about accumulating facts and solving problems, but about expanding the boundaries of the possible, about discovering new ways of thinking about reality that would have been inconceivable to previous generations. The question of what happens inside a black hole thus becomes a metaphor for the broader human quest to understand our place in the universe. It represents our desire to penetrate the deepest mysteries of existence, to find meaning and pattern in the apparent chaos of the cosmos, to discover the fundamental principles that govern everything from the smallest quantum particles to the largest structures in space. Black holes teach us humility in the face of the unknown, while simultaneously inspiring us to push beyond the boundaries of current knowledge. They show us that the universe is under no obligation to conform to our expectations or desires, that reality operates according to principles that can be mathematically precise, yet conceptually alien to our everyday experience. Until we understand black holes, we may never fully understand the universe itself. They are cosmic laboratories where the deepest laws of physics are written in the language of curved space-time and quantum mechanics. They are gateways to questions about the nature of information, consciousness, and reality that may ultimately transform not just physics, but our entire understanding of what it means to exist in this strange and wonderful cosmos. The holes in our understanding are not failures of science, but invitations to discovery, challenges that call us to develop new mathematics, new physics, new ways of thinking about the fundamental nature of reality. Black holes are not just objects to be studied, but mirrors that reflect back to us the depth of our ignorance and the vastness of what remains to be discovered. In the end, black holes may be the key that unlocks the deepest secrets of the universe, revealing connections between mind and matter, between information and geometry, between the quantum and the cosmic that we can barely imagine. They may show us that the universe is not a collection of separate objects, but a unified quantum system where everything is connected to everything else through invisible networks of entanglement and information. What happens in a black hole? the answer may be nothing less than the key to understanding what happens in the universe itself. The secret code that explains how space emerges from quantum entanglement, how time arises from correlations in information, how consciousness connects to the deepest structures of reality. Until we crack this cosmic code, the universe will remain fundamentally mysterious, a puzzle with pieces scattered across the vastness of space and time, waiting for future generations to assemble them into a complete picture of existence itself.